Hello everyone and welcome back to this next lecture in the machines lecture series, and this is where we had left off in the previous lecture where we had talked about how we can introduce the mechanical component of the simulation. When I say mechanical component, the reason is we are simulating an electrical motor, and when we are simulating an electrical motor we need to simulate the mechanical part, which means we need to simulate the speed, we need to simulate the mechanical torque, and we also need to simulate the electrical torque that produces this mechanical torque. So in briefly, which I had written was that these are some of the mechanical variables that we need to either calculate or we need to bring in through simulation. Omega m, and the m here, the subscript m here, it's not really a subscript but it's just another variable, determines the mechanical speed of the motor. This is different from the angular frequency of the supply, which is denoted by omega, which is equal to 2 pi f, where f is the line frequency, which is either 50 Hz or 60 Hz. Tm is the mechanical torque, which is the output. So this is the actual working power which is produced by the motor. And then there is Te, which is the electrical torque, which is the torque which is produced by the motor due to the interaction of the fluxes. Right? And therefore, quite obviously, the difference between these two torques will be resulting in the acceleration, using which we can find out the speed. So we now said that to introduce this speed, we have to start introducing the speed, and to introduce the speed we came up with the variable which is theta m. Theta m is the mechanical rotor position. Right? So therefore what we said is that at any instant of time, if we define an axis of our rotor, we can define with respect to that axis what is the angle made with respect to some stationary axis. Right? More about this later soon. And we said, of course, since we are defining this rotor angle is merely the integral of the rotor speed, which is integral omega m dt. So the question then arises, how are we going to introduce this into our equations which have been written here? Now the equations written here have been written using the electrical laws, and we had said that one way we can consider it is we can look at the potential impact of the rotor position on the value of these parameters. That is, do these parameters change with respect to the rotor position, and if they change, how can they change? So we had already looked at a potential, is it possible that the stator resistance and the rotor resistance changes with the rotor angle? And we found that that's not the case. The stator's, the resistance and the rotor resistance will change as the machine heats up. So therefore, as the rotor starts rotating and remains in rotation, it will start heating up, and that heating effect will change these resistances. But these resistances will not be directly impacted by the rotor angle. Therefore, our conclusion was that the stator resistance and the rotor resistance can remain as constants. With that, we decided to move on to the self-inductance and the inductances, which is for now the self-inductance of the stator and the self-inductance of the rotor, LS and LR. Right? Now, for that reason, we had gone into the definition. That is, we said that the inductance as defined can be defined in this form, that is, the current multiplied by the inductance is equal to the flux linkage. So therefore, we can say that if 1 ampere current flows through an inductor of 1 Henry, the flux linkage will be 1 Weber per turn. Right? This is the definition. This is how inductance is defined. Of course, this definition really doesn't really help that much. So therefore, we decided that what if we go into the flux, the actual flux path? So we say that supposing, for example, we consider this inductance to be made of N turns. And these N turns are carrying this current I. Of course, it's the same current I. This is capital, this is small. But this is therefore resulting in an ampere turns of Ni. Right? Simple as that. Current flowing through a coil with N turns produces an ampere turns of Ni. Therefore, this ampere turns, which produces this flux, if we can calculate the reluctance of the flux path, right? If we know the reluctance of the path through which the flux flows, then we can say that the flux is equal to the ampere turns divided by the reluctance. And therefore, once you know the ampere turns by the reluctance, we can also say that if we can calculate the flux, we know the flux linkage as flux multiplied by the number of turns. So quite obviously, we can just say Ni squared divided by reluctance. This is equal to the flux linkage. And from there, we can also calculate the inductance. But what I'm trying to say through this entire through this argument is that we can now go back to drawing the flux path in the machine and determining what could be a change in the inductance with respect to the rotor angle. So before I continue, and that's what I'll discuss in this lecture, before I continue with this lecture, as usual, a little bit of brief background, that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses which you can access on my website, pythonpowerelectronics.com. So this is my website, and in this website, if you click on the button Learn, it will take you to the page with the courses which I have currently. So the very first course I have is Simulating Power Electronic Circuits using Python, and in this I talk about the basics of how you can use Python and Python Power Electronics to simulate power electronic circuits. And the next course I have is Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and packages such as the signal package within SciPy to analyze and design filters for power engineering applications. The third course I have is called Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can use Python and Python Power Electronics to simulate magnetic components like inductors, coupled inductors, and transformers. And the fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as the Python control package to analyze and design controllers for power engineering applications with the specific case of a single phase converter to connect it to a single phase grid. And the very last course I have is called Why Specialize in Power Electronics. This is a free course which is targeted towards either junior undergraduates or towards high school students who are yet not decided their specialization, or rather the domain in which they want to specialize in. So this course talks about some of the challenges and opportunities available in power electronics so that any young engineer can use this as a guideline if he wishes to specialize in this domain. So in order to access any of these courses, you can click on either of these buttons. All these courses are hosted on two platforms, Udemy and Decibel Labs. You can click on any of these buttons to access the course. The link for this page is provided in the description of this video. If you're interested, please do check out the description. So with this, let me get back to my lecture. So as I said, the objective is that we are going to try to figure out, using the flux path, what could be the impact of the rotor angle on the inductance. And here there'll be a little bit of discussion on construction, not too much, but just a little bit to give you an idea of how the construction of the motor can have an impact on the inductance with respect to theta. So for this, let me go back to the diagram of the induction motor which I had. So this is what we've been using throughout as our reference. And this is a squirrel cage induction motor, as I already said. It is single phase. You can see there's a main winding. We are not yet talking about this auxiliary winding, so forget that this exists. There is a squirrel cage and there is a main winding. So for now, this stator here contains the stator winding, which is of course a set of windings. Now these windings are wound along the length and across the circumference. So assume that these windings are actually passing through the entire circumference of the stator. As these windings pass through, they are producing a magnetic field throughout the length of the stator, and this magnetic field associates with the rotor throughout the length. So you see this rotor, which is mounted within the stator, is now within the magnetic field of the stator. And because of that, there is an induced EMF and there is a torque. We'll get to that soon. But what is important is that, let us say we take a cross section of this. So I'm going to cut it along the length and let us take a cross section. And let's assume this rotor is also embedded within. So if we were to look into this from the left, so we are looking into the motor and we take a cross section, what you will see is two concentric circles denoting the stator, an air gap, and then another circle which denotes the rotor. Right? So for now, I will use a very simple program called GPaint. I had tried to use LibreOffice Draw, but I think it was too heavy. That's why there was a crash last time. So let's start drawing. Alright, so let these three circles denote the inner one denotes the rotor, the outer two denote the stator, and of course between these, that is between this part, is the air gap. So let us suppose that this denotes a cross section of the stator, cross section of the motor. That is, this is what we are looking at. So if we are slicing this in this manner, we are slicing it, we get a cross section. Now this cross section that we are looking at, now let us assume that there is a winding. Now in reality, this winding is fairly complex, and it's actually, winding is an entire subject. Motor windings are an entire subject on its own. It is fairly complicated. For example, there is a way in which windings are distributed throughout the stator. So for example, you will have slots throughout the stator, and there will be windings that are passing through and going all over the circumference. So this is something that happens throughout. So for example, if we take a winding, it will come across this, complete its path from the bottom slot, and then complete to another slot. This will then extend on through the circumference until we complete the coil. So this is fairly complex. I can't go into that much depth. But what is important is, if we take the simplest possible case of just a single winding that represents this stator coil, just a simple winding. So for example, let's say there's one slot at the top, one slot at the bottom, and there is a conductor passing through. And if there is this conductor passing through, we can say that even if it is distributed, let us say that these two slots represent the entire stator winding, right? So we can therefore use such a simplified representation to at least draw the flux path. So let me go over here and tell you what I mean. So I'm going to draw two circles. So one at the top and one at the bottom. So these two circles will represent the slots. Alright, let me color one of them. So let me just color this one. When I mean color, it means I am trying to denote the direction of the current which is flowing through the slot. So for example, what I mean is, there is a conductor which is passing through the slot, another conductor passing through the slot, and these two are forming the coil. So we are winding a coil of n turns passing through these slots, and which is actually going through the entire circumference of the stator. So let us say that the current in this slot is going into the slot, into the page, and here it is exiting the page, right? Just a convention. You can consider the other way as well. So if I were to say that the current in this slot is passing into the page, then by using right hand thumb rule, we can determine the flux in this path. Now, in order to understand the flux in this path, again, it is important to understand that the flux is always concentric to the conductor. This is, I would say, one of the experiments conducted by Hans Christian Ørsted all the way back in 1821, where he determined that a current flowing through a conductor will produce concentric magnetic flux lines, and these magnetic flux lines will extend and will keep getting weaker. So we can say that there will be magnetic flux lines which are concentric around this particular conductor, right? So let's draw some. I'm going to use the free hand here. So let me draw one very small one, and let me keep drawing. Again, if I had good softwares, it would look better, but the main idea here is just to get an idea of how the flux goes. So for example, these are flux lines, and there are advanced softwares which you can use to map out the flux produced in any machine, right? I do not have access to them because they are all proprietary, but this is an example of concentric flux lines produced by this conductor. Now, we see that the path which is formed by these flux lines, passes through two types of medium. The first medium is the iron of the rotor. Of course, it could be iron, it could be an alloy, it could be laminated alloy. There are several things. Doesn't really matter. What matters is that this magnetic material has a high permeability to flux. Then comes the air gap. The air gap has a low permeability to flux. Typically, the permeability of iron is around 500 to 1000 times that of air. Usually. They can be even higher if you use special alloys. It could be lower if you're looking at some other types of alloys. Depends. Again, we come into the rotor. The rotor is again a magnetic material. So therefore, the permeability within this rotor is also very low. So we have two types of paths. We have a high permeability path for the flux, and we have a low permeability path for the flux. So let us neglect this very first one, because this flux path, and this reason why I wanted to draw this is because not all the flux that is produced by the stator will link the rotor. This can be considered leakage flux. For example, there will also be flux which is leaking into the air in this manner, right? Flux is fairly complex. There will be always some flux which leaks into the air. These flux which leak into the air and do not associate with the rotor are considered leakage flux. Let us consider the other ones. Now, we can draw the same. Here it's important to understand that because of the direction of current, the current is flowing into the page. If we use right hand thumb rule, that is, we grab the conductor with the right hand, encircling the fingers with the conductor, the direction in which the fingers encircle the conductor is the direction of the magnetic field. And therefore, because of that, we will see that the direction of the magnetic field is clockwise, right? The direction of this magnetic field is clockwise. You can verify it yourself. Now here, exactly the same thing happens. So let me just draw that as well. The first one is of course useless, and just in case, let me draw one here as well. This is leakage flux. Not very nice. And let me then draw a little one here. And another one here. Again, bad drawings, but this is the best I can manage, right? This is how far I can get with free software in Linux. So I probably need another drawing software as well, but let me not bother about that. So these are very similar. And here, because the current is coming out of the page, if we use right hand thumb rule, again, we'll find that the direction of flux is exactly the opposite of this one. So here it will be counterclockwise. And here too, exactly the same argument. The flux has several segments. It has a high permeability part and it has a low permeability path. The useful flux of the stator is that which links with the rotor, and therefore that passes through the magnetic material, through the air, and the magnetic material of the rotor. So let us now talk about what can happen. Now again, as I said, flux can be in a very complicated. The flux path is very complicated, and it is usually not so uniform. There is fringing, there is non-linearity, there is non-uniformity, there is all kinds of things. I can't do all that. We have to assume a very simplified path for the flux. So if we consider the path for the flux, we will see that the flux always finds the path which is the least reluctance. Always. Water will flow through the path of least resistance, current will flow through the path of least resistance, so will flux. At least most of it. So if it were to flow through this air, the path which is the least in length and the least in reluctance is the path which is least in length. And the path which is least in length is along the radius, right? And therefore you will see that all these fluxes typically in the air gap are radial, right? And the reason for that is simple. Along the radius, the length in the air gap is the minimum. And because the length in the air gap is the minimum, that is the path of the least reluctance. Because remember, reluctance is directly proportional to the length of the path in that material. So again, this is an assumption. Most of the flux will flow along the radii. But there will always be some flux for various reasons which will flow in other directions. Let us neglect that for now. So if we say that this flux were to flow through these two paths, there are two different segments. One which is 1000 times more higher permeability than the other, right? The permeability of air is 1000 times less than that of the magnetic material, or rather the iron material. So if I were to approximate this, I could say that the reluctance of this entire flux path is dominated by the reluctance of this air gap. The reluctance of the air gap here and here will be the main source of reluctance in this entire air gap. Alright, that can be said. So now the next question you might ask is, why am I doing all this? The reason why I'm doing all this is, using these calculations that we did here, it is now possible to calculate the flux linkage for a current flowing through the stator. Right? How do you do that? If there was n number of turns flowing through this slot, or rather n number of turns of the coil in this slot, the ampere turns is going to be n into I, and I is the current. And if the ampere turns is n into I, then in that case, if we divide n into I by the reluctance of the flux path, we can calculate the flux. As I said, the reluctance of the flux path can be calculated by considering all the segments, that is the path through the magnetic material, path through the air, and back here again. But as I said, we can make an approximation because the reluctance of this air gap is the significant part in this entire reluctance. Remember, we are talking about 1000 times greater reluctance with respect to the magnetic material here. And therefore, if we say that this reluctance is the highest, we can calculate the reluctance of this flux path and this flux path and equate that to the total reluctance of this flux path. Therefore, if we have the reluctance and we have the reluctance of air, because we know the length, we know which is the length of the radius, right? We know the length of the air gap, and we know the permeability, which is the permeability of free space, and we can also calculate the permeability, which is calculate the cross-section area by assuming a length of the stator. So therefore, it is possible to calculate the reluctance. If we calculate the reluctance, then the next part is we can calculate the flux. If we have the flux, we know the flux linkage, right? Because we already know the number of turns. And if we know the number of turns and the flux linkage, then it is only normal to say that we can calculate the inductance. So using this entire schematic, not very nice schematic, I do realize it's a bit messy, but using this schematic, we can calculate the inductance of the stator. This is the self-inductance of the stator. Why? Because we are calculating the flux linkage of the stator because of the current flowing in the stator. Later on, we'll do the other way around. That is, we'll calculate the flux linkage of the rotor due to the current flowing in the stator. Then we are calculating the mutual inductance. But that comes later. So, now this lecture has gotten pretty long, so I will stop here. But the main objective behind all this is to show you that you can use, so far we have not ever gone into construction of the motor. We have only used equivalent inductances, we have used this equivalent circuit, and we have considered just estimated the parameters from the ratings of the motor, assuming that we conducted no load test and block rotor test, right? Nowhere until now have we gone into the construction of the motor. But now we are talking about the construction of the motor. Why? Because I want to show you the flux path, and I would also like to show you how the flux path can impact the inductance. Now, there are several types of inductance. Some will not be impacted, some will be impacted, and there are also some cases in which even the self-inductance can be impacted, and those are in the case of salient pole rotors. But all that will come gradually, not right now. Now, with this, I'm going to end this lecture. If you have any doubts, please do post either in the comments or send me an email or message me on social media, whichever is your preference. If you have a better software, go ahead and try it out. I will also look for a better drawing software. I do realize this is not very convenient. I've been using Paint in Windows. This is significantly tougher because I can't erase anything. So I will also look into that. Otherwise, in the next lecture, we are going to talk about we're going to bring in the concept of rotor angle, and we'll talk about how as the rotor rotates, what would be the impact of these flux lines. Why? The reason is, if we can say that these flux lines will change, and we can also denote that these flux lines changing will result in a change in the inductance, then we can determine that the inductance is impacted by the rotor angle. That is what I'm trying to get at. So, thank you so much for listening, and see you next time where we will get into that detail. Goodbye for now.